Welcome back. So we continue with section 0.2.1, and now we move to the notion of closed sets and related concepts. So in a topological space, a subset is said to be closed if its complement in the set is open, so belongs to the topology. A neighborhood of a point is a set containing an open set containing the point. So same thing as in metric spaces. And usually the set of neighborhoods of a point x is denoted by calligraphy q of x. And it's easy to prove that a set is open if and only if it is a neighborhood of all its points. This is something trivial actually that we proved in second year. The interior of a set is the biggest open set contained in the set. So it's the union of all open subsets of the set. It's denoted by a circle. The closure of a set is the smallest closed set containing the set. So it's the intersection of all closed sets containing the set. So it's denoted by a bar. The boundary of a set is the difference, the set theoretic difference between the closure and the interior. So it's a bar minus a circle. So you see that all these concepts that we studied in the case of a metric space actually do not depend directly on the notion of distance. So they just rely on the notion of an open set. Now, convergence. Okay, let us revisit the notion of convergence. First, let us see what happens in the metric case. If we have a distance, then we have the notion of closeness between 2 points. So 2 points are close together to each other if their distance is small. So in a metric space, we say that a sequence xn is converging to element x if xn can be made arbitrarily close to x for all n large enough. And this is given by the following condition that you know from first year. So we say that xn converges to x if for every epsilon positive, there is a certain rank starting from which the distance between the elements of the sequence and the limit is less than epsilon. So we can think of epsilon as being the accuracy of the approximation. Okay, so this is the definition. Now, we want to extend this definition to the general case of a topological space. So let us rewrite this definition in a slightly different form. The fact that the distance between xn and x is less than epsilon, means precisely that xn belongs to the ball, the open ball of center x and radius epsilon. And now, the open ball of center x and radius epsilon is a neighborhood of x. And any neighborhood of x contains such a ball by definition, because a neighborhood contains an open set and therefore contains such a ball. So we can restate this condition of convergence in the following way. For every neighborhood U of x, there is a certain rank starting from which all the elements of the sequence are in that neighborhood. Okay, why we are doing that? Because now this condition actually does not involve directly the notion of a distance. So we can take this, it rather depends on the notion of neighborhood. And the notion of neighborhood depends on the notion of an open set. So we can take this as the definition of convergence in a general topological space. Okay, so this is the definition. Now, I must say that in a general topological space, weird and unfamiliar situations can happen. And I will give you an example now. A sequence may converge to several points. And this is an example. If we equip R not with the usual topology, but with the finite complement topology that we described in the previous video, and consider the sequence of integers, okay, 1, 2, 3, etc., then we claim that xn converges to every point of x, so it doesn't have a unique limit. How do you know that? We go back to the definition. So we consider a neighborhood U of x. Of course, we may we assume that U is open. Otherwise, you replace it by a smaller one. So we can assume that U is open. Since it's not empty, then by definition of the finite complement topology, the complement of U is finite. So here we are assuming that U is open. We can always assume neighborhoods are open. And so it's a finite set. Therefore, we take an integer n0 bigger than the maximum elements in the complement, because this is a finite set. So we can always take the maximum exists. So if we choose n0 large enough, then what do we have? Then n actually belongs to U for all n bigger or equal than n0. Okay, why? If n is bigger or equal than n0, then n is bigger than the maximum. If n is bigger than the maximum, it cannot belong to the complement. So n does not belong to R without U, so it belongs to U. Just logic. Okay? So we proved, according to our definition of convergence, that this sequence converges in this particular topology to all points of the real line. So it has infinitely many limits. Okay, so this is unfamiliar actually. But I must say that this rather pathological condition does not happen in metric spaces, and more generally does not happen in what we call Hausdorff spaces. And now I'll define Hausdorff spaces in a moment. Okay, so limits are unique in metric spaces. Okay, now let us consider this result. Actually, it was proposition 1.8 in the course on metric spaces, if you remember. This is a characterization of the closure of a set. This is actually a bar, not a. Sorry for that. This is a bar. So it didn't appear in the. Okay, so if we consider three conditions, x belongs to a bar. Second condition, every neighborhood of x intersects or meets a, and there is a sequence in a which converges to x. When we had a metric space, I recall from second year, all these three conditions were equivalent. This was proposition 1.8 actually. Now in general topological spaces, 1 is still equivalent to 2, and 3 implies 1 and 2. So we don't have equivalence between 2 and 3. This is not difficult to prove. Now, if x is metrizable, then 1 implies 3. And the three conditions are equivalent. And this was proposition 1.8. Okay, so please correct that this is a bar, not a. A bar, the closure of a. So it's very important because we shall use it later. Okay, to prove that a point is in the closure of a set, we prove that every neighborhood of that point has an intersection with A. Same proof carries actually. If you look carefully at the proof of proposition 1.8, you can just rewrite it. And one, in a general, in an arbitrary topological space, 1 does not necessarily imply 3. And here's an example. Okay. Equip the closed interval 0, 1 with the countable complement topology. So the sets that are open, what are the open sets? Are the empty sets, and sets whose complement is countable, is a sequence. Okay. The first claim is that a convergent sequence in this topology, we are not considering the usual topology, we are considering this special unfamiliar topology. So a convergent sequence in this topology is eventually constant. What do I mean by that? Eventually constant means that it's constant from certain rank. Okay. Let us prove this claim. Okay, suppose that xn converges to some limit a, according to our definition of convergence. And consider the set of elements of the sequence that are distinct from A. Of course, this is a subset of the range of the sequence, so it's a countable set. Okay, so the complement of F is an open set, and it contains A, right? Because A is not in F, right? So the complement of F with respect to 0, 1 is an open neighborhood of A. It's an open set containing A. Okay, so since xn converges to A, then from a certain rank, xn will belong to this neighborhood. Now, what does it mean that xn does not belong to A, to F? It means that xn is not distinct from A. So xn equal to A. So from a certain rank, xn is precisely equal to its limit. Okay? Now, once again, this does not happen in the usual topology. This is a particular mode of convergence. It's very restrictive. Okay? So this proves the claim. A convergent sequence in this weird topology is eventually constant. Okay. Second claim. Consider A to be the semi-open interval 0, 1, open at 0. Then we claim that 0 is in the closure of A. Okay, how do we know that? We use the previous proposition. To prove that 0 belongs to A bar, we must prove that any neighborhood of 0 meets A. Now, the singleton 0 is not open. Why? Because the complement of 0 is A, actually. So it's uncountable. So the singleton 0 is not open. Okay, it's not a surprise. So therefore, any neighborhood of 0 cannot be equal to 0. So it contains a point different from 0. And therefore, it meets A. Right? Trivial. So 0 belongs to A bar, and this proves claim 2. However, no sequence of A converges to 0 in this topology. Why? Because if xn is a sequence in A that converges to 0, then xn will be 0 according to claim 1 from a certain rank. But then it will be outside A because 0 is not in A. Right? So here we have 0 is in the closure, but there's no sequence in the closure of A, but no sequence of A converges to 0. Okay, so this is a counterexample. A corollary of proposition 0.3 is the following about density, actually, of sets. Density is very important. So if we consider the following conditions, so we have a topological space and the subset A of X, and consider the three conditions. A is dense in X, meaning that A bar is X. Condition 2, every non-empty open set of X meets A. Condition 3, every X, small x in the space, can be approximated by a sequence in A. So what do we have here? 1 is equivalent to 2, right? This is just because according to the previous proposition, and 3 implies 1. And if the space is metrizable, 1 implies 3, and therefore the three conditions are equivalent. Okay, now we come to Hausdorff spaces, a very important class of spaces. Hausdorff space in French is called séparé. Why? The Hausdorff condition means that every two distinct points of X can be separated by two disjoint open sets or two disjoint neighborhoods. So whenever X is different from Y, we can find a neighborhood U of X and the neighborhood V of Y that do not meet disjoint. A Hausdorff space is also called a T2 space. So these are the axioms of separations that you may have studied in general topology. And the first almost trivial result is that a metrizable space is a Hausdorff space. Why? Okay, so first choose a distance d that generates the topology of that space. Now, d is not unique. You may choose any distance you like as long as it generates the topology which is given. Since x is different from y, then the distance between x and y is strictly positive. So we take r to be the distance over 2. And now it's easy to check that the ball of center x and radius r and the ball of center y and radius r, of course, they are disjoint by the triangle inequality. And each one is a neighborhood of, so the first one is a neighborhood of x, the second one is a neighborhood of y. Okay, so you may draw a figure, actually. Therefore, by contraposition, a space which is not Hausdorff is not metrizable. And now this explains why in the examples of the last video, many topologies were not metrizable. Why? Because they are not Hausdorff. Simply. If you look back at these examples, for example, the indiscrete topology is not metrizable because it's not Hausdorff. Okay. The finite complement topology on an infinite space X is not Hausdorff and therefore not metrizable. Same thing, because any two disjoint non-empty sets meet in this. Why? Because we can reason by contradiction. If two open sets are disjoint and they are not empty, then in this special topology, the complements are finite, right? So the union is finite. Therefore, the complement so the union of the complements, the complement of the intersection. But if the intersection is empty, then the complement is the whole space X. So we would have X is finite, but we assume that X is infinite. So we get the contradiction. So in this special complement, finite complement topology, any two open sets non-empty necessarily meet. Okay, so we cannot find two disjoint open sets, right? So it's not Hausdorff, right? Now, what happens if the space is finite? As you may check, if the space is finite, then the finite complement topology is precisely the discrete topology. You may check that. And therefore, it's metrizable in this case. We know that. So this is why we assume that the space is infinite. Okay, this is an example. Now, in chapter 5, so we said that metrizable implies Hausdorff, but the converse is not true. And I'll give you an actual example in chapter 5. We may have Hausdorff spaces that are not metrizable. Okay. And a useful result in Hausdorff spaces, which was true in metric spaces in second year, is that finite sets in a Hausdorff space are closed. How do you know that? It's enough to prove that singletons are closed. Okay, how do I prove that the singleton X is closed? I look at the complement. How do I prove that the complement is open? By proving that the complement is a neighborhood of all its points. So I consider a point in the complement, so Y is different from X. Therefore, by the Hausdorff condition, I can separate X and Y by two disjoint open sets U and V. Therefore, since U and V are disjoint, then V is contained in the complement of U. And since X is in U, then the complement of U is in the complement of X. So we found an open set, an open neighborhood of Y contained in the complement of X. So this means that the complement of X is a neighborhood of Y. Since Y was arbitrary, this means that the complement of small x is a neighborhood of all its points, and therefore it's open. Okay. And we have now a weaker condition than the Hausdorff conditions called the T1 condition. A topological space is called a T1 space if singletons are closed. So what do we have? So T2 implies T1. Okay. So we have actually other conditions of separation. We have T1, T2, T3, T3 and a half, T4, T5. You usually study such things in a second course on general topology. Okay, but we shall not need them in this introductory course. So we just need the T2 condition, the Hausdorff condition, which is very important because one of the reasons why we like Hausdorff spaces is that limits are unique. Limits of sequences are unique, as we shall see now. Of course, so T2 implies T1, but the converse is not true. So we could have a T1 space which is not T2, and this is the case with of the finite complement topology on an infinite set. Okay, so as I was saying now, in a Hausdorff space, sequences converge to at most one point. So why this is so? It's very easy. Because suppose that the sequence xn converges to two distinct points x and y. Okay, now separate x and y by two disjoint neighborhoods u and v. Since xn converges to x, then starting from a certain rank n1, xn is in u. But since xn converges to y, then xn will be in v starting from another rank n2. Therefore, if we take n large enough, so bigger than the maximum of 1 and 2, then we would have xn belongs to u and v, but u and v are disjoint, so it's a contradiction. So limits are unique if they exist. Okay. Now we move to the very important notion of continuous functions. So as usual, let us revisit the condition of continuity in matrix spaces, and then we will find a definition that which works in a general topological space. So if you have a function between two matrix spaces x and y, and you consider a point small x in the source space x. Okay, what does it mean to say that f is continuous at the point x? As you may know, since now we have the notion of closeness of 2 points in y, because you have a distance on y. So f is continuous at x if the limit of f of y as y tends to x is f of x. Or otherwise stated, f of y can be made arbitrarily close to f of x for all y sufficiently close to x. And this is now, as you may know, is captured by this definition. So a function f between two matrix spaces is continuous at a point x if for every epsilon positive there exists delta, such that if the distance between x and y is less than delta, then the distance between their images is less than epsilon. So the same idea of convergence actually. So epsilon is if you like, is the accuracy of the approximation. So the distance can be made arbitrarily small, provided the points are sufficiently close together. Okay. So this is the definition of continuity at a point of a function between matrix spaces, which generalizes actually the notion of continuous function between R from R to R or from Rn to Rm. Okay, just in the case of R, this is just the absolute value of x minus y, and this is the absolute value of f of x minus f of y. Okay, but we don't need to use the absolute value. We can, the same definition works for any distance. And now we want to generalize this to, we want to define the notion of continuity of a function between two topological space. So we have to do what we did earlier, is to reformulate this in terms of balls and neighborhoods. So the fact that, and now of course I must say that you can put less or equally, it doesn't change anything, because if it's less than epsilon, it's less or equal. If it's less than or equal than epsilon, then it's less than 2 epsilon. Okay, so you can put here 2 epsilon, 5 epsilon, anything, because if epsilon is arbitrary, then 5 epsilon is arbitrary as well. So we can put here less or equal, same thing, doesn't change, as you may know. Now, let us reformulate this condition in terms of balls. Okay, so in a metric space, we have an equivalence between 5 conditions. F is continuous at x according to our definition, this first definition. Second condition, for every epsilon positive, there exists delta positive, such that the image of the ball of center x and radius delta is contained in the ball of center f of x and radius epsilon. It's exactly the same thing, because if you look at this, what does this mean? It means that f of y belongs to the ball of center f of x and radius epsilon, right? We encountered this idea before. And this condition means that y belongs to the ball of center x and radius delta. Okay, so it's clear that we can rephrase, if you like, the condition of continuity by this one, in terms of balls. And now, since balls are neighborhoods of their center, and any neighborhood of a point contains a wall of that center, then we can restate condition 2 in terms of neighborhoods. So for any neighborhood V of f of x, we can find a neighborhood U of x whose image under f is contained in V. So just the same thing. But we can also restate the notion of convergence in terms of continuity in terms of convergence. So if xn, so f is continuous at x if and only if xn converges to small x, then the image of xn converges to the image of f. Okay. So this is what we call sequential continuity, and I will say something a little bit later about that. And the last condition that we proved actually in Math 2201, it says that if xn is a sequence converging to x, then there exists a subsequence xnk of xn whose image under f converges to f of x. Okay, so actually we proved that in Math 2201 by a circular reasoning. So we proved that 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, and 5 implies 1 by contradiction. It's very interesting. Actually, you can look at the proof, and it's very important actually. But now, if you look at all these 5 conditions, I will not prove it here in this video. Look at the lecture notes of Math 2201. So the only condition among these 5 that does not involve distances is condition 3, because it only involved neighborhoods. Okay, it's equivalent to continuity in metric spaces. So as usual, what we do? We take condition 3 as the definition of continuity of f between 2 topological spaces. So a function f between 2 topological spaces now is said to be continuous at a point x if for every neighborhood v of f of x there exists a neighborhood u of x whose image under f is contained in v. This is just condition 3. So now we have the notion of continuity of a function at a point. Now continuity everywhere, continuous on the whole space. Yeah, here. So, and of course, as I said, we can replace open neighborhood by a neighborhood, so it doesn't matter actually here. So a function is continuous on the set x if it's continuous at every point of x. And we have a very important result that a function is continuous on the whole space if and only if, pay attention, the inverse image under f of any open set of y is an open set subset of x. And it's also equivalent to the condition that the inverse image under f of any closed subset of y is closed on y, you know, of x. So you should know that from the course in general on metric spaces. It's not difficult to prove actually. I will not prove it here, but this is a very important characterization of continuity. Continuity not just at a point, continuity on the whole space, which means continuity at every point. Okay. Now I will end this subsection with a quick review about compactness and connectedness. But let me tell you something actually that I didn't appear in the slides. If you go back to proposition 0.7, we have now the notion of continuity of function between topological spaces. Now, what if we consider this condition 4? Xn converges to x implies f of xn converges to f of x. This is a very important condition, but it's equivalent to continuity in metric spaces or in metrizable spaces, but it's not equivalent to continuity in a general topology between general topological spaces. So this condition 4 is called sequential continuity. Okay, so we have 2 notions now of continuity. Continuity, as we defined here in this by this condition, and sequential continuity. Sorry, it didn't appear in the slides, but it's in the notes. We have to distinguish continuity and sequential continuity. So what do we have? Continuity implies sequential continuity. The converse is true in metrizable spaces, but not in general topological space. So we may have a sequentially continuous function which is not continuous, And I gave an example in the lecture notes, but it didn't appear here. Okay. Okay, now we go back to compactness, because also here we have several notions of compactness. We have the open covering definition. So a subset of a topological space is said to be compact if every open covering has a finite subcovering. You know that from second year. This is the definition. This is what we call compactness. Okay, and we know that in Rn a subset is compact if and only if it's closed and bounded in any of the usual distances that you can put on Rn. Okay. Now we have another notion closely related to the first one, but independent. It's called sequential compactness. Sequential compactness, so a topological space is said to be sequentially compact if every sequence of X has a convergent subsequence. Now, in Math 201, we know that sequential compactness is equivalent to compactness. Okay? Now, in an arbitrary topological space, the two notions are independent. So we may have a compact space which is not sequentially compact, and the sequentially compact space which is not compact. Okay? Now, I will not give counterexamples, but you can find them if you search on Google. I may give one example later when we talk about the product topology. Okay, so in an arbitrary topological spaces, we have two independent notions, compactness and sequential compactness. But we know from Math 201 that these two conditions are equivalent in a metrizable space. Okay, and this is a non-trivial result. It's hard to prove, actually. And I don't always give the proof in class. Okay, so in metrizable spaces, so we have two characterization of compactness in metrizable spaces. Okay, the open covering definition and the sequential definition. Okay, and in chapter 4, I will give another interesting example where compactness is equivalent to sequential compactness. Okay, but as well as also it's not trivial, so I will not give a proof. Section 4.6. It's a deep result of functional analysis, but I will not. It's the proof is in the notes, but I will not give it here. Okay, now why do we like compactness? Because compactness works very well with continuity, and we have two basic results linking compactness and continuity. The first one states that the image of a compact space under a continuous function is compact. So continuity preserves compactness, if you like. And the second result, which is very important as well, is that if we have a continuous function or compact set, then f is bounded from above and from x to r, so it's real valued function. So any real valued continuous function from a compact space is bounded from above and below, and it achieves its bound. So it has a maximum value and a minimum value. So sorry, here the result didn't appear, but okay. So I think you know this from second year, but it's very important and it's a fundamental result in optimization problems. So if you want to search a maximum for a maximum, the maximum need not exist always. But if the space is compact and the function is continuous, then it has a maximum and a minimum as well. Okay, and last concept is that of connectedness. I'll just give a quick definition. I'll not give examples because you shall not deal with connectedness in this course, actually. But you should know that intuitively a set is connected, topologically space is connected if it's one piece, so it cannot be broken down into two disjoint open sets, if you like. An equivalent condition is that a subset A of a topological space is connected if whenever B and C are open disjoint sets of X and A is contained in the union, then necessarily A is contained in one of them and not the other. You should know also that the union of connected sets having a point in common as well is connected. Okay, and you should know that the connected subsets of R are precisely the intervals. And we proved in the topology course that the image of a connected space under a continuous function is connected as well. So continuity not only preserves compactness, but it preserves connectedness as well. Okay, and this concludes this video and section 0.2.1 from metric spaces to topological spaces. So thank you for your attention. And in the next video, I will finish section 0.2 about general topology.